Hi, I'm Melissa Hartwig, and I'm going to be doing a problem modeling a piecewise falling object. I've included a Word document with the post that I'm hoping you can print so that you can follow along as we go. So here we go. A ball weighing 23 grams is thrown upward from an initial height of 2 meters with a velocity of 12 meters per second and k equal to 0.30. When the ball reaches its maximum height, a small parachute opens, increasing k to 1.2, and the ball falls to the bottom of an 80-meter cliff. Find v sub t equals 0, the maximum height reached by the ball, the total time t sub f that the ball is in the air from when it's thrown to when it reaches the bottom of the cliff, and state the piecewise function v sub t. I've drawn a small diagram to help me see what it is that's happening in the problem, written out all the important information, including our differential equation dv dt equals g minus rho v, where rho equals k over m. I have gravity separated for each problem because when the ball is thrown in the air, gravity is pulling down, and when the ball is falling, gravity and velocity are going in the same direction. I've gone ahead and solved for my rho 1 and my rho 2 based on the k values and the m value that are given in the problem. And so to start, in order to find v sub t, the first thing we have to do is plug the information that we have into our differential equation and solve for v. So 9.8 minus 1.3043 v is the equation that we're going to be starting with. We're going to get the v term onto the same side as our dv dt term because clearly this is not a separable equation. And that will lead us to dv dt plus 1.3043v equals minus 9.8. And so what we need to do now is find our multiplier. And we start with p sub v, which is equal to rho, which is equal to 1.3043. And then to find our multiplier mu sub v, we do e to the integral of rho, which in this case is e to the integral of 1.3043. This is with respect to dt, and we get e to the 1.3043. T is our multiplier. We're going to go ahead and multiply that through our entire, this differential equation here, So we'll have e to the 1.3043t dv dt plus rho times e to the rho t times v was minus 9.8 e to the 1.3043t. Now from here we should recognize that what we have here is dt of e to the 1.3043 tv equal to the minus 9.8 to the e term. And our next step is going to be to differentiate both sides of this equation. We know, we're doing this with respect to dt, we know that the integral of a derivative just cancels each other out, so we get e to the 1.3043 tv equals, now we're going to divide our rho term into our 9.8 to get its integral there, and that comes out to be minus 7.5136 e to the 1.3043t plus c. We'll go ahead and divide through by our e term to solve for v, which will give us minus 7.5136 plus c e to the minus 1.3043t. And that's our general solution, which we're going to go ahead and put in our parameter that v sub 0 equals 12, so we can solve for our c. And we'll have that 12 equals minus 7.5136 plus c e to the 0, which we know is just 1. So we're going to add the 7.5136 to both sides, and we'll get 19.5136 equals C. And so our model equation will be V sub t is equal to minus 7.5136 plus 19.5136 e to the minus 1.3043 t. And so this is our model equation that we are going to use to find V sub t equals 0. So for V sub t equals 0, we're going to plug 0 into our equation. So we'll have 0 is equal to minus 7.5136 plus 19.5136 e to the minus 1.3043 t. Then we're going to solve for t. So we'll add the first part to the other side. Then we're going to divide through by the 19. So we'll have 0.38504 is equal to e to the minus 1.3043 t. Take the natural log of each side. And then divide through by our negative row term there, and we'll get that t is approximately equal to 0.73174 seconds. So we now know, and I'm just going to put it down over here, that V of 0.73174 equals 0. Box it out so I don't accidentally erase it. All right, and so that solves for A. A is done. So now we're going to use this information here that we have found to find the maximum height reached by the ball. And to do that, you need to remember that position, or in this case, height, is equal to the integral from t1 to t2 of the v sub t that we found with respect to t. And so we are going to plug in what we have. So we're going from 0 to 0.73174, our equation of minus 7.5136 plus 19.5136 e to the minus 1.3043 t with respect to t. Excuse me. And solving that integral, we'll get minus 7.5136 t plus minus 14.96098 e to the minus 1.3043 t. We're going to evaluate that from 0 to 0.73174. All right. So that works down to minus 5.4980 minus 14.96098 e to the minus 0.95441. And that's just distributing this number here into here. I'm just trying to save some time. And we're going to subtract from that 0 minus 14.96098 e to the 0. This goes and simplifies down to minus 5.4980 minus 5.7606 plus 14.96098 96098. And all of this is equal to 3.70238. Now this is h. This is the distance that the ball goes from here to here. Our maximum height, though, will measure from here to here. So in order to get that, we simply need to add our initial height plus the height that we just got, and we'll get our h max. And that is going to be 2 plus 3.70238. And so h max is equal to 5.70238, and that is in meters. And so that's how we find the maximum height that the ball reaches. Now, for the next part of the problem, we need to find out the final time it takes total for the ball to go from being thrown to landing at the bottom of the cliff. Now, to do this, we need to solve the differential equation for the time when the parachute is open, which is different because we do have a different k involved, which gives us a different rho. We're also using a positive gravity. So we're going to set up the equation again. dv dt is equal to 9.8 minus 5.2174 v. We're going to get our v term and our dv dt term on the same side. So we're going to make that a plus 5.2174 v. Our piece of v is our rho, and our mu sub v is e to the integral of rho dt, which is equal to e to the rho t, which is equal to e to the 5.2174 t. We'll distribute that through our equation. Okay, recognizing, of course, that this is now d dt of e to our rho times v. And then we're going to go ahead, integrate both sides, and we're going to get e to the rho times v equal to our 9.8 divided by our 5.2174, which is going to give us 1.8783 e to the 5.2174 t plus c. We're going to divide through by our e term to solve for v. So we get v is equal to 1.8783 plus c e to the minus 5.2174 t. And now what we're going to do is we're going to use this parameter to solve for our c term. And so we're going to say that 0 equals 1.8783 plus c e to the minus 5.2174 times 0.73174, which is going to simplify down. Well, we'll move this over, so we'll have minus 1.8783 equals c e to the minus 3.8178. We're going to divide through, and we get that c is equal to minus 85.4701. And so, just so we have it up here, I'm going to go ahead and write our model solution. V sub t is equal to 1.8783 minus 85.4701 e to the minus 5.2174 t. All right, now we're going to use that to solve for the final time for the ball by using the equation we used before of h equal to the integral of v sub t dt. Only this time we know our height. Our height is actually going to be our 80-meter cliff plus the height that we found maximum for the ball, which was 5.70238. Sorry. And so our h is going to equal 85.70238. So we'll set up our equation. 70238 is equal to the integral from our starting v sub t here, because we're starting here and going here for this part. We've already accounted for the time in the air here, is 0.73174 to t sub f of 1.8783 minus 85.4701 e to the minus 5.2174 t with respect to t. I'm going to leave this here for now. I'm going to go ahead and solve the integral. So we're going to have 1.8783 t minus, plus 16.3818 e to the minus 5.2174 t, evaluated from just shy of a second to our final t. I'm going to skip over some of the algebra that I know you guys are able to do, and we're going to come down to where we have 85.70238 is equal to 1.8738 t sub f plus 16.3818 e to the minus 5.2174 t sub f minus 1.73112. We're going to subtract the 85 over so that we have 0 equals 1.8738 t sub f plus 16.3818 e to the minus 5.2174 t sub f minus 87.4335. And what we're going to do is we take this equation, we plug it into our graphing calculators under the y equals, go into the table, plug in some numbers. You're looking up and around the 50 area generally for a problem of this type, I would say. And then when you get a good idea, you go in, find your 0 point, and this one we find our t sub f is equal to 46.661 seconds. So that is the amount of time it takes the ball to go thrown up into the air and to float down to the ground. So the final thing that we're asked to do is to state our piecewise function v sub t. So we'll say v sub t is equal to minus 7.5136 plus 19.5136 e to the minus 1.3043 t. And that is for 0 less than or equal to t less than or equal to 0.73174 and 1.8783 minus 85.4701 e to the minus 5.2174t for 0.73174 less than t less than or equal to 46.661. And there you have it, modeling a piecewise falling object